Okay, so this is an electric field question. Charged particle, a charged metal sphere, cannot particle, is isolated in space. Measurements of the potential is given. Okay, let's zoom out a little bit. Okay, the measurements of the potential is given. So you can see that it's a sphere. So that means that the radius is around 2 cm. Okay, make sure you take note of the cm here. So the radius is 2 cm. By making reference to the electric field, explain why the electric potential is constant for distances between x equals to 0 to 2. Okay, so this this is within the sphere, okay, a sphere, so which is a conductor because it's a metal sphere. So the thing about this is that within a sphere, E field is going to be 0, okay, and potential is therefore going to be constant, and that is the what the question is asking. Okay, you can see that it's constant here, so need to first explain that it is going to be 0. So you can probably say that um, within a conductor, okay, which in this case the metal sphere is a conductor, the electric field is 0. Okay, my guess is this should be 1 mark. Then we need to explain why why the electric potential is constant. Since electric potential, since electric field, okay, equals, now just draw in, minus dv dr. Since electric field equals to minus dv dr, and E field is 0, right? Therefore, V must be constant. That's about it. Okay. Next, calculate the charge of the sphere. So this, you can see that this is a sphere. The formula for potential here is going to be V equals to 1 over 4 pi epsilon naught Q over R. So we'll be using that. And this can be used starting from the surface of the sphere. So we'll be using at this location. Okay, within a sphere, no. Okay, it's going to be constant. It's always, although R is taken from the center of the sphere, but you can see that the 1 over x curve, right, only starts from the surface and towards infinity. Okay, so here you can read that it's going to be 3.6 volts. So now we'll calculate. So using V equals to 1 over 4 pi epsilon naught Q over R, we want to find Q. Okay, 3.6 equals to 1 over 4 pi epsilon naught Q over 0.02. Okay, because it's going to be 2 cm. So just press on your calculator, times 8.85 times 10 power minus 12 times 0.02. So from here, I get my Q as 8.0. Okay, we'll do 2SF here because you can see that the values that are given to you here, right? 2.0 is going to be 2SF. Okay, so the later parts are also 2SF, so it will make sense to be in 2SF. Okay, so I'll just put more SF as the intermediate steps. 729 times 10 to the power of minus 12, which is approximately 8.0 times 10 to the power of minus 12 coulombs. Okay, so how you know you are roughly correct is because you can see that the next one is also around in the region of 10 power minus 12. So we know that we should be pretty close in terms of the magnitude, okay, in terms of the power here. Okay, so next one, calculate the electric potential at 4.0 cm if a particle of this charge is placed at 6 cm. So in other words, now we have one positive particle or positive sphere of 8.0 times 10 power minus 12 coulombs. Okay, and at this point is 4 cm away. And at this point, we are going to get a negative charge. Okay, a negative particle, negative 7.2 times 10 power minus 12. So you are supposed to calculate the potential at x equals to 4. Okay, so we know here it's going to be 2 cm. Here it's going to be 4 cm. So because potential is a scalar, we can just scalar sum them. Okay, total electric potential is equals 1 over 4 pi epsilon naught 8.0 times 10 to the power of minus 12 divided by 0.04 plus 1 over 4 pi epsilon naught negative 7.2 times 10 to the power of minus 12 over 0.02. Okay, let me just key onto my calculator. Divided by 0.0. You can see that to speed up your calculations during exams, you can factorize this out on your calculator and only multiply them later. Okay. Now take note that the negative sign is included because potential is a scalar. Okay. So unlike forces and fields, we ignore the negative sign because we want to take the magnitude and direction separately. Okay. So this is going to be a negative potential because 4 cm is pretty big. Okay, so divide by 4 divided by pi 10 power minus 12 times 10 power minus 12. So you should get about negative 1.4387. 1.4387, approximately negative 1.4 volts. Okay, so the particle then accelerates from rest at x equals to 6 cm. Without any calculations, describe the acceleration in terms of its magnitude and direction. So without any calculation, okay, so basically it's going to be a positive and a negative charge here now. Okay, so the negative will of course be attracted. So we are supposed to describe the acceleration. Means in other words, you need to understand how the forces changes. Okay, because F equals to ma, we can identify how the acceleration changes based on the changes in the resultant force. And in this case, the resultant force is going to be the electrical attraction, okay, force of attraction between the positive and the negative. So how I would write this will be, okay, you can see that it will be based on the force, and because it's attractive force, okay, so you'll go from 6 cm, go towards the 2 cm, okay, go towards x equals to 0, and the force will only increase because the E field here is increasing. Okay, so the particle will accelerate towards x equals to 0 cm because unlike charges attract. Okay, the question never asks for the reason, so we can ignore that also, but I'm just putting it here for you to understand. Next, we need to talk about the next we'll be talking about the magnitude. Okay, this part is a direction, so it's 1 mark already. So the magnitude, so talking about the magnitude, what will happen is that as the particle moves towards x equals to 0 cm, the electrical force of attraction increases, hence acceleration increases. Maybe to be clearer, magnitude of acceleration increases. Okay, so we see we are tackling by Newton's second law, F equals ma. Okay, next, calculate the kinetic energy of the particle after moving a distance of 2 cm. So this is conservation of energy. So we are calculating after it moves from 6 cm to 4 cm. So what will happen is that there will definitely be a gain in Ke, which must come from a loss in EPE. Okay, so loss in EPE equals gain in Ke. Okay, so did they say, okay, it's released from there, so the initial K is going to be 0. Okay, you can see from here. So the loss in EPE will be initial minus final, 1 over 4 pi epsilon naught we'll just take 8.0 negative 7.2 over 0.06. Originally, they were 6 cm away. Initial, because loss is initial minus final, so I'm taking the initial minus the final over 0.04 multiplied by 10 power minus 12. Yeah, I took this out so that you write less inside. And in this case, you will square this because both charges are of 10 power minus 12. Okay, so in a way, you can see you write less things here. On the calculator, you can even consider taking these two out. You can see that they are going to be the same, Q1, Q2, and then put it out here as well. Okay, so you can write less and calculate and press the calculator less things. Okay, less careless and faster some more. So this is equals to half mv square minus 0. Okay, oh no, we don't need half. We don't need the half mv square because the question only asks for the ke. We can ignore all this and basically just write the kinetic energy, the final kinetic energy minus 0. Good enough. So the final kinetic energy, okay. So basically, okay, let's press the over calculator. Multiply by 8, multiply by negative 7.2, divide by 4 pi epsilon naught times 10 to the power of minus 24. I will get 4.3161 times 10 to the power of minus 12 joules. So 4.3 times 10 to the power of minus 12 joules. Calculate the work done by the E field on the particle in part 2. Okay, so the gain in the KE or the loss in EP will actually be the same as the work done by the E field. So basically, it is more of the same. Okay, it's actually more conceptual. Let me check. Okay, so I'm not so sure why the loss they ask you to calculate, but basically the work done by the E field. Oops. Basically, the work done by the E field, okay, is going to be just the gain in KE. So it also will be 4.3 times 10 power minus 12. Lastly, a particle has mass of 3.9 times 10 power minus 25 kg. That's pretty small, and the same charge. Calculate the initial speed if it was launched from x equals to 4 and make a U-turn at x equals to 8. So basically, there's a plus. That's the original 8.0 times 10 power minus 12 coulombs. Okay, this one is not clear whether the original particle is there. Okay, I will say that. Okay, I will guess that the particle from part D, okay, this one, and part C. Okay, means there's a if a particle. Okay, there's a if here. So originally it wasn't there. So I would say that the particle is not to be considered for part E, especially because of the word another particle. Okay, so we assume that the first particle is not there. We have to assume that. Okay, you could try calculating if it was there. So the question I would say that it's not very clear in this sense. So let's take it as the first particle is not there. So from x equals to 4, this is what happens. X equals to 4 cm, it will go to x equals to 8 cm before it U-turn. Okay, and this will happen because there's an attractive force towards the positive. So at here, we need to find the initial speed, and at here, the v is equals to 0 because it's a U-turn. It's at the maximum point, v is equals to 0. So again, this is going to be a conservation of energy. So from x equals to 4 cm to 8 cm, there is definitely a loss in KE and a gain in equals to a gain. Let's erase this part. Equals to the gain in EPE. Okay, so loss in KE, half mu square minus 0. EP, again, 1 over 4 pi epsilon naught. 8.0 and negative 7.2, same thing, divided by gain is final minus initial. So final minus initial. Okay, we have to be disciplined on the initial minus final or final minus initial. Okay, so this is going to be 0.04. But and then remember the multiply by 10 power minus 12 square. Okay, because we didn't put it inside. So from here you can get your initial speed. Okay, let me just press the calculator again. So 1 divided by 0.08 minus 1 divided by 0.04 multiply by 8 multiply by negative 7.2. Okay, divide by 4 pi epsilon naught. And then finally multiply by 10 power minus 12, minus 24. Okay, so you will get half, that is half mu square. Okay, maybe I just put it here first. Half mu square equals to 6.474 1 times 10 power minus 12. Then we find what is the speed. Okay, times 2 divided by the mass, which is given 3.9 times 10 power minus 25 kg. Then remember the square root. I get around 5.76. Okay, maybe put 2SF. Okay, maybe I will just put the full one first. 5.76 2 times 10 to the power of 6, which is approximately 5.8 times 10 to the power of 6 meters per second. So that will be the final answer here.